And I'm live. That is pretty cool. Today is 2nd of February 2026, Monday, and with that, let's begin. Screen is not stuck, which is like a good part somehow, which is like the minimum requirement. Okay, and spanning trees. That is what we are going to read about today. Yeah, cool. We need spanning trees. Like, yes, we need sometimes spanning trees. And I think there was a problem when I didn't know, when I wasn't aware about that there are things called spanning trees. There was a problem in which we had to calculate. I think there were multiple houses in a town, as there are, and there were roads connecting them, random roads connecting them, and we had to find the minimum number of roads to connect all the houses in such a way so that the total length of the selected roads is smallest and each house is either directly accessible or indirectly accessible from another house. So yeah, everything is connected and cool. Hello. Yes, I just started. I today I started late because there is my voter ID card is being made, so I had to go there and give my documents. Yes, yes. Even though other like someone might not understand the things I am saying in that, it is just there to help me. And yeah, David Goggins all the way. Hello. I may just get updates from you. Uh, yes, everything is cool if you are like asking about me. And how are you? Well, I probably will have a voter ID card now. Okay, shit. I mean, yeah, as a responsible citizen, we should be voting, I guess, so that there is something. Huh, that is cool. Cool stream ideas. I mean, there is only like what can we do in his streams? I'm great. Just crack. Yes, like that is cool. You are a contributing member of the society. You earn money and give. Wait, I don't think you give taxes on bounties because it is not a official income. It is just like Paytm, UPI or something, right? You don't have to give taxes on bounties. It would be crazy if you had to give taxes on bounties. And spanning trees. When we exchange, we do okay. So like there is a account in which you get money in dollar, and then when you want to spend it as rupees on that exchange, you give taxes. Mm, that makes sense. Yep. Spanning trees. A spanning tree of a graph consists of all nodes of the graph and some of the edges of the graph so that there is a path between any two given nodes. Like trees in general, spanning trees are connected and acyclic. Usually there are several ways to construct a spanning tree. So yes, for example, consider the following graph. This is a spanning tree. Wait, nope, this is not a spanning tree because this should be a tree first of all, and it is spanning but it is not a tree because there are cycles. We cannot go back. We can go in a loop, but in a tree we do not have any loops. And the number of edges is 1 minus the number of uh, nodes. So yep, one spanning tree for the graph is as follows. Yes, this is one spanning tree, the way, and yes, we can reach any one node from any other node either directly, like 1 and 2 are directly connected, or indirectly from 1 to 5. 1, 2, 3, 6, 5. Cool. The weight of a spanning tree. The weight of a spanning tree is the sum of all the edges. The weight of a spanning tree is the sum of its edges. Edge weights. For example, the weight of the above spanning tree is 3 plus 5, 8 plus 9, 17 plus 3, 20 plus 2, 22. 22. Cool. A minimum spanning tree is a spanning tree whose weight is as small as possible. The weight of a minimum spanning tree, for example, for this graph is 20, and such a tree can be constructed as this. Yep, we have our normal spanning tree, a tree which has like spanning properties where each node is connected to every other node directly or indirectly, not indirectly. And a minimum spanning tree is one where the sum of these weights is as minimum as possible for any possible spanning tree. Wait, okay. And also USDC or digital coin from Binance Finance or Trust Wallet as well. Okay. And since new budget, there have been increase in tax rates. There have been, I thought in last year's budget there was a decrease in tax rates for like normal income. And hello, yep, this is competitive programming handbook, the one you were asking about. If so, where can I get a PDF first? Wait, I replied to your comment, and no, this is free. You don't have to buy it. And hello again. You can just search CP handbook. And also one more thing, the one that I'm using, look at this. This has 300 pages. And if you search CP handbook and go to this website, ces.fi, fi because Finland, this has 296 pages because this one was written and was drafted in 2018. So to get a like newer version, if that is what you want, you can go to ustaco.guide cph.pdf. This one has the latest, or not latest, but a later version of that book. This has 300 pages and this came out in 2019. Comparatively newer. Here, no cooking stream. Nope. Yeah, but this time foreign exchange is changing a lot. I haven't seen like this budget which came out yesterday. German, there was something, I was doing something, so I was not able to wake up early, but yes, I will make them like normal, regular streams. Okay. Yes, go there, newer version. File type PDF file, all. Did you know about this? File type PDF. Like, are you making a reference to the joke where we say PDF dot file or something like that? All digital coins are going in red. What does that mean? Even ETH and ETH. I don't know much about crypto and all that, but yes, ETH and Solar coins are going down. Search. Okay. Shit, going red. Uh, their stocks are going down. Suggestions. Okay, nothing. Okay, there's nothing. Google doesn't know this, so maybe this might be an insider joke. Any, okay, any type of book and then PDF file. For example, let's say I have a book, War and Peace PDF, something like this. War and Peace PDF. Wait, this one is longer. Somehow this one is longer. Because yes, the text is like very big. Anna Pavlovna, Vasily Kuragin, Prince Vasily Kuragin. Yes. It might. I think I can trust him. Maybe. I think I can trust him. But okay, like back to spanning trees. Page 140. Is 141 prime? Prime. 141. No, it is not prime. It is divisible by 3. 3. into 47. 3 into 47 is 141. 120 plus 21, yes. Uh, 3 into 47 is 141 and 47 is 47 prime. 47 looks like a prime number. Yes. 47 is prime. 3 is not prime. Yes. It's a Google dorking method. Dorking. To get direct PDF link access. If you want PDF, kidding. It is a famous technique for getting books by try using it with O'Reilly books as well. I do not have a O'Reilly book. I have Hoarder books, classic, fingerprint. This is a famous technique. I've been using tips for books, research papers since 2019. Yeah, I have also. And then search techniques. Okay, if you want book, then you can go to Library Genesis. Just type the name of any book. For example, Outliers is by Malcolm Gladwell. Gladwell. Shit. They don't have a book. Why don't they have? I think the spelling is wrong. Malcolm. Yep. You can sort here by PDF. Here, EPUB, electronic publication, and you can look for PDF also here. Cool, and download in different languages. What is this? Portuguese. If like that is the kind of thing you are into. Yeah, that is cool. And for research papers, you can go to this scihub.sc, which is not working right now. Here, just write the name of a research paper. Uh, let's say Turing or Einstein 1905 relativity. I think it was on that. Yes, Brownian motion. He proved that uh, there are molecules on the electrodynamics of moving bodies. Copy this, type the name of the paper, and you will not find it. Shit. You can request this article through usually more than 90%. Maybe we have to copy the link, but yeah, you can get papers from this website. You can get it. Is like right now not working. The one that I use is this one. It is also not working, but you can get papers from this website. Learning React from O'Reilly. This I have. Shit. Yep, they upload books. Shit, O'Reilly, yes, programming books. We can get them. That is cool. Okay, and back to minimum spanning trees. In a similar way, maximum spanning trees is a spanning tree whose weight is as large as possible. The weight of a maximum spanning tree, for example, in the example graph is 32. 5 plus 6, 11 plus 5, 16 plus 9, 25 plus 7, 20, 32. Cool. Note that a graph may have several minimum and maximum spanning trees. Yes, because they might give them same final maximum weight. So the trees are not unique. Yes, it turns out that several greedy methods can be used to construct minimum and maximum spanning trees. In this chapter, we discuss two algorithms that process the edges on the graph ordered by their weights. We focus on finding minimum spanning trees, but the same algorithms can find maximum spanning trees by processing the edges in reverse order. Makes sense. There are two algorithms, Kruskal and Prim's algorithm. First, Kruskal. In Kruskal's algorithm, okay, this algorithm was published in 1956. Wait, this algorithm was published in 1956. 1956 is very old, and this is for graphs. When did the concept of graphs was invented? When did this even occur? 1736. That is very old. What were people doing with graphs? Euler. Okay, it was Euler. The concept of graphs in mathematics was invented by Leonhard Euler in 1736. 1736. Euler. When was he alive? Leonhard Euler, polymath. Wait, he does not look like this. He looks like this. One of his eye has a defect. He came to life in Switzerland. That is cool. 1707, and died in 1783. 1707. 1707. Francisco Goya. When was he born? 1746. So yeah, they were like close enough. He made model city land masses and bridges, and as vertices and edges, proving a path crossing each bridge was once impossible. So that is cool. In 1736, we have had the concept of graphs. That is cool. Okay, so Kruskal's algorithm, the initial spanning tree only consists of the nodes of the graph and does not contain any edges. Then the algorithm goes through the edges ordered by their weights and always adds an edge to the tree if it does not create a cycle ordered by their weights, like minimum to the maximum edge, weight of a edge. The algorithm maintains the components of the tree. If initially each node of the graph belongs to a separate component, yes, okay, the algorithm maintains components of the tree. Components means that if there are parts of graph which are not reachable by other parts of graph, then those parts are called components. And initially, since we do not have any edges in our whole tree, then each node act is a component because they do not have anything connected to them, so they are not reachable from each other. So initially each node is a component. Always when an edge is added to the tree, two components are joined. Yes, because if we add an edge which does not join two components, that means that new edge is connecting two things which are already connected, so they are making a cycle. We do not do that. Finally, all nodes belong to the same component and a minimum spanning tree has been found. We can write this. Yes, let's write an algorithm for this. Pushkal tree.cpp update synchronize and shade. Cool. And here we will have a Kruskal thing. This takes in an adjacency tree and shit, my bad. I have to fix something. Like this happens every day. Keyboard shortcuts. Modified keys for the USB keyboard. The caps lock should act as control. Include bits.stdc purpose.h and then paste std, and we'll have our adjacency vector which has n things and vector. Each element is of type vector and adjacency. Why are we defining it? Cool, makes sense. We will define this in the main function. And what is n? That is also a good question. Now we have our adjacency vector. Do we need an adjacency vector? What we would need, or what would be more beneficial, would be a list of edges here. Yes. Edge, an edge equals a tuple of three integers. And this thing takes in a vector of edge reference called edges. Vector is edges, and yeah, that is good. And here one more thing, uh, edge dot first thing is connected, let's say, to edge dot 2 and edge dot 3. The third thing is the width. So after getting this, we will sort this edges dot begin and this dot end with a custom function where the type is edge A and edge B. Yes, this does not come inside this thing. D I bracket. Return. How do we get shit? Yes, makes sense. How do we get some element from a tuple? This is like always a bit difficult, or like I don't get this. How do we get? I think we have to use the get function with here giving the index of the thing that you want to get smaller than b dot get to. How to get element from a tuple CPP? Get, okay, standard get this, and inside it takes in the tuple. Return get the element number 2 for a. This has to be smaller than get element number 2 from B. And after this has been sorted, we also have to keep all the components. We'll just now go edge by edge, and instead of keeping track of components, we will keep track of which edges have not been connected. So a boolean vector, a boolean vector will do. A boolean vector will do. Connected size would be this dot size, and initially everything is false. Nothing is connected to anything. Then for auto left, right, or first, second, and wait in edges if we need if we want to check if the current edge that we are joining, at least one of them should be not connected. So if f connected f If F not connected or not connected, S, if at least one of them is not connected, if both of them are connected, this would be false and this would be false. If at least one of them is connected, then we will have this in our final edge. How do we say that we are going to take this edge into our final spanning tree? We will create a new vector of edges called spanning, and if we are going to add this thing into our spanning tree, spanning dot pushback first, second, and w, and let's also have long wait equal 0, wait plus equals w, and connected f equals connected second equals, both of them are connected to something. That is good enough. Vector return spanning here also. Cool. And let's add some things to our edges. What? 1, 2 connected by 3. We'll just add stuff to our edges. 8. Yes. What would be the fastest way to look at both of these things like at the same time? If I full screen this, continuous scroll, yep, and then connect it to, cool. Okay, it does not move. This is our tree. Here we have 1 and 2 connected with a weight of 3. Yep. Then we have 1 and 5 are connected with a weight of 5, and then we have 2 and 5 connected with a weight of 6. Then we have 2 and 3 connected with a weight of 5. Then we have 5 and 6 connected with a weight of 2. And then 3 and 6 connected. 6 connected with a weight of 3, and then 3 and 4 connected with 9. 3 and 4 connected with a weight of 9. And finally, wait, did we add 3 and 6? We did add 3 and 6. Then finally 4 and 6 with a weight of 7. 4 and 6 with a weight of 7. In here we have 1, 2, 3, 4, 5, 6, 7, 8 things, and here also we have 8. So cool. What we should get is a spanning tree that looks like this, maybe. And here this will also print the weight. Let's use printf weight or the minimum spanning tree is this, and what is this? This is weight. This is long, cool. Okay, and we will call this function and auto spanning is call this crucial function on edges, and now we would like to print this tree. How do we print this tree? for auto first, second, and wait, do we need wait? Yes, why not? Run this on spanning and print if this and this are connected by a wave of this, let's say first, second, and W. Compile and run, and we see 5 and 6 are connected. 5, 6, 1, 2. We have 4 edges, which 4 is not right. Shit, makes sense why this would fail. It makes sense. This would fail because let's say we have 4 nodes, 1, 2, 3, and 4, and we connected these two and these two, and then the next edge was going to connect this and this. Well, these two already have been connected, but they are not reachable from each other. But our algorithm would not connect them because this one has a connection and this one also has a connection. But these should be connectable because they are not part of the same component. So, shit. So we just have to check which component do these things belong to. And how do we keep track of components? Do we run a DFS every time? How do we keep track of components? Well, there are now one less. This is one component, one more, one more, one more. And when we connect these two, now this is one component. These two have become one component, and there is one component here, one here. And then this, now we have one component here, one here, and a single one here. Then if we connect this, then we have in total two components. How do we keep track of components? This is one component and this is the other one. Components. We just have to check what what the two nodes that we are connecting, whether they belong to the same component or not. And running DFS is not a right choice, is yes, does not make sense, because we would have to run DFS for every edge that we are going through, and in total we will go through at maximum all of the edges. Let's say we'll go through all of the edges in total. Let's say there are E edges and N nodes, so we will go through E edges, and if we were to run DFS for each edge that we add, then each DFS algorithm, how long does it take? DFS goes through each node, so E into N, and total time complexity would be E into N, which is not very good. So there has to be a better way of keeping track of components. Either we can see, we can have a mapping from these nodes, like for each node we should be able to tell which component does it belong to, or we can have a data structure which stores the components, and looking at the component we can tell which nodes does it have. Since we want to look at which component does the node belong to, so we would have something like this: mapping from node to components. C, from nodes to components, right? And we cannot just, yeah, let's say we have 3, 4 things. This one belongs to component 1, 2, 3, 4. When we connect these two, if we are going to have a vector, whose component are we going to change? Maybe we can have a set. Maybe we can have a set. Maybe we can have a set. Makes sense. Maybe we can have a set. This component stuff is too much work. This component thing is too much work. If we have a set where one set denotes one component, and whenever we connect two components, we take their or or and, which is same in this case because a single edge does not belong to two components at the same time. So we take their no their and or are going to be different, but their union and or are going to be same. Union is or. Yeah, they are not going to have any overlap. Their and is going to be 0. That is the case. So, but that is still is too much work because we would have to go through all the elements of a component to add them to each other, which is again not very efficient, too much work. Yep, not very efficient, too much work. And the real problem comes when, let's say, we have two big components, one big component here, which has a lot of nodes connected to each other in some way, another component here, and then when we connect two things in these components like this, then each of these nodes is going to be accessible by any other nodes in that other component. How do we update that? Like if we have a mapping, like you were saying, from node to the component by maybe node number 1, node number 2, then we would have to know update node number of every node in this component to a common node number, maybe 1 or 2. But if we have a mapping from component to node, then we would have to go through component to component looking up nodes. Yep. And there doesn't seem to be a better way to keep track of the nodes, to keep track of the components. The algorithm maintains the components of the tree. Initially, each node of the graph belongs to a separate component. Yep, keeping track of the components is work because, yes, like in this example, exactly in this example, where we have a bunch of nodes in one component and a bunch of nodes in the other component, whenever we connect two nodes, any nodes, every node in this component and every node in this component has to be updated in some way so that they know that they are now connected to new nodes. If you want to know from nodes point of view which component they belong to, but if we are using a component major order where given a component we can look at all the nodes which belong to it, in that case, since we do not have a priority on the node, that is, we cannot just look at a node and find out which component it belongs to. We would have to go through all the components to find out which component does a given node belong to. And I think it is better It is much better. No, it is also not much better, because for the first edge, for edge number one, there are going to be n components, or yes, n components, because there are n nodes, and initially each node is a component in itself, nothing is connected. So for the first edge, we will have to go through all of the nodes. Then for the second edge, we would have to go through n minus 1 components. For the third edge, we would have to go through n minus 3 n minus 2 components, and so on till the eth edge. We would have to go through n minus e plus 1 components. So in total, the time complexity, let's say e, what if e is also big? Yes, then the total, let's say e equals n, or similar to n. So we are adding things till 1, and our total time complexity would be n into n plus 1 by 2 big O of this number. If we were going to go through a component major order, and we can implement any one of these, component major or node major. So what is the best way to keep track, to keep to keep your hair while sleeping, to keep rats away from car, to keep uh, track of the components in a graph in Kruskal's algorithm? Disjoint sets, union find data. The best way to keep track of components in Kruskal's algorithm is by using disjoint sets. DSU efficiently manage merge, union, and checks for component representatives, enabling on near E log E or near E log E complexity to prevent cycles while building the minimum. Okay, DSU, I have heard this word before. Disjoint sets. Okay, a set is a collection of elements, and disjoint, I guess, means that there is not a single element which belongs to two sets at the same time, so that every set is disjoint. They do not have any common elements. And union, maybe union, their union. Okay, if we take all the elements in two sets at the same time, initial vertex begins as its own disjoint set. Find, and yes, this is literally like analysis. This is cool. Hello, mate, you are from Australia or from UK? Because people there speak mate, they say mate, or mate in one, like this. Chess. Union operations, find operation determines which set a node belongs to. How do we find? Yes, which is similar to looking at a node and finding out which component does it belong to, which set does it belong to, allows the algorithm to check if two nodes belong to, and nodes in an edge are already connected. How do we do the find operation? Union operation, when we connect two components, they become two single component. Wait, shit, that makes sense. That makes sense. Maybe, no, maybe we cannot. No, I thought maybe, well, we will have a list of these sets, in each set representing a single component. And initially, there would only be a single node in each set. And whenever we connect any two sets, any two components, we would just take a union and form a bigger component like this. But in this case, the problem is finding which set a given node belongs to. We would have to go through each set, and we would have to search through each set looking for our current two nodes. So that is time consuming. But the union part, I think, is union part would be a bit faster. But I thought maybe instead of going through all the nodes, maybe we can have another list where let's say number 2, number 3, where the first element is going to be a pointer to the node that this element is connected to, and second element is going to be the pointer to the node to which this second node is a part of. But still, whenever we do a merge operation, in that case we would have to update a lot of elements to their new singular node, which is again very time consuming. Optimization: use path compression and union by rank size makes operations nearly constant time. This structure is superior to alternatives like BFS or DFS. This does not seem superior, this just seems same. Lol. Yep. Hello, Indian person. Like, I'm also Indian, but yes. Today I started streaming late because I had to give my documents to the government to make me a voter ID card. So yes, Indian. Negate Negating, but have they given a like a written algorithm? Yes, it does work. Implementation, yes, they have, but they are not saying how they are looking for the thing. When implementing Kruskal's algorithm, it is convenient to use the edge list representation of the graph for finding out the next smallest edge which has not been used. The first phase of the algorithm sorts the edges in the list in m log m time. Yes, after this, the second phase of the algorithm builds the minimum spanning tree as okay, that is like very abstract. If A and B node are not connected, then connect them. That is very abstract. The loop goes through the edge list in through the edges in the list and always processes an edge A, B, where A and B are two nodes. Two functions are needed. The function same determines if A and B are in the same component, and the function unite joins the components that contain A and B. The problem is how to efficiently implement the functions same and unite. One possibility is to implement function same as a graph traversal. Yes, that would be DFS or BFS to check if we can go from node A to B. However, the time complexity of such a function would be n plus m, and the resulting algorithm would be slow because the function same will be called for each edge in the graph. Yep. We will solve the problem using a union find structure that implements both functions in log and time. Thus, the time complexity of Kruskal's algorithm would be m log n after sorting the edge list. What is union find structure? Okay, they are going to tell us. That is cool. So, yep, here they are just telling we are manually going through Kruskal's algorithm in this whole part, in this whole section. Why does it work? It is, and you can also watch a video about this thing, Kruskal's algorithm. There is a cool video. I think the name of the person is Spanning Trees. Yep, Spanning Trees. This video, this is pretty cool video. You can watch this one also. How to calculate a minimum spanning trees. He has animation, which is cool. Now, how does it work? Let's go through this. This is a good question. Why Kruskal's algorithm works? Why does the greedy strategy guarantee that we will find a minimum spanning tree? Why does it guarantee that we will find a minimum spanning tree? Let's theorize before reading why does it work. Let's theorize why does it work. So our algorithm says we have a list of edges in sorted order of their weight. These are all the edges in sorted order of their weight. Weight is represented by their height. So if we are looking at the first edge, this let's say connects these two, we will connect it, and then we look at another edge and we connect two more things, and then we look at another edge, we connect two more things, and then we look at another edge, and we see that this one connects these two, so we connect these two, and then we look at another edge, and this edge, let's say, is connecting these two things, and this is a cycle, so we will not connect this. But what if it was better to remove something else and use this? Okay, now we have a cycle, right? Now we have a cycle, and whatever, how big, no matter how big the cycle is, we, according to Kruskal's algorithm, we are not going to use this edge. And now maybe the actual minimum spanning tree might require this edge and the removal of some other edge from the cycle. But since we have gone in the increasing order of edge weight, all the other edges in this cycle have either the same weight as this one or a weight that is smaller than this. So in this cycle, the best edge that we can remove, which has the highest weight, is this one, which is being removed by the Kruskal algorithm. Therefore, Kruskal algorithm works. And then yep, we skip this, we go to the next one, and let's say it is this, and we connect it, and we have a minimum spanning tree. Let us see what happens if the minimum weight edge of the graph is not included in the spanning tree. Minimum weight edge of the graph is not included in the spanning tree. For example, suppose that a spanning tree for the previous graph would not contain the minimum weight edge 5 to 6. Let's say this was not contained in the actual minimum spanning tree. We don't know the exact structure of such a spanning tree, but in case it has to contain some edges, assume the tree would be as follows. Since we do have to connect 5 to something, we will connect it. However, it is not possible that the above tree would be a minimum spanning tree for the graph. The reason for this is that we can remove an edge from the tree and replace it with a minimum weight edge 5 to 6, because we added 5 to 6 edge because it had a smaller weight, and if we are going to remove that and add something else, it will have either the same weight or a weight that is greater than the weight of 5 6. This produces a spanning tree whose weight is smaller by removing the other thing that we connected and using 5 and 6 here. For this reason, it is always optimal to include minimum weight edge in the tree to produce a minimum spanning tree. Using a similar argument, we can show that it is also optimal to add the next edge in weight order to the tree, and so on. Hence, Kruskal's algorithm works correctly and always produces a minimum spanning tree because we are always going in increasing order of the tree. Hello, quite late stream today. Yep, it is a competitive programmer's handbook, and yes, late because I was doing something else. Like I had to go to the government to give my papers, and look at this, 144 is square of 12. That is cool. And now we will look at a very cool thing. How do we implement a function which works fast and which has this functionality? Given two nodes, it tells us whether these two nodes belong to the same component or not, and then another function which combines the two components that A and B are connected to. So yes, how do we implement this algorithm faster? And they say that there is a thing called union find structure. We will use that. Let's see. A unified structure maintains a collection of sets. A collection of sets. Okay. Each set representing a component, I suppose. The sets are disjoint, that is, no single element belongs to the to two different sets, that is, they do not share components. These sets do not share elements, so no element belongs to more than one set. Two O log n time operations are supported. Okay, the unite operation joins two sets and it is going to take log n time. That is crazy. And the find operation finds the representative of the set that contains a given element. And they are saying the claim is that these two algorithms run in log n time. That is crazy. In a unified structure, and also this, a given element, they have a footnote. The structure represented here was introduced in 1971. Okay, shit. This structure came out in 1971, introduced in 1971 by Hopcroft and J.D. Ullman. Okay, but this algorithm itself, Kruskal algorithm, came out in 1956. 1956. And this in 1971. That is like 15 years. So, okay, that is cool. So that shows like things do not go, things take time and they happen in steps. Later in 1975, R.E. Turgeon studied a more sophisticated variant of the structure 64 that is discussed in many algorithm textbooks nowadays. 64, what is that? Okay, shit, that is a footnote. ACM Turing Award, what is the full form? Computing machines. CM is computing machines, but what is A? Association of Computer Machinery, I think. Computing Machinery. Association for Computing Machinery. They also give the award, ACM Turing Award. Coloring. Shit. We were at page number 144. Almost. Okay, so this thing came out in 1971 and a more sophisticated version came out in 1975. Yep, that one. Oh yeah, I was also learning about lambda lambda calculus, and I am still unable to get over how the fuck conditions work in it. Lambda calculus. What do you mean lambda? L like in maths or in programming? Seems like this book won't give me any such trauma. Who is the author? Author is Antti Laksonen, Finnish person. Finnish as in from Finland, not that he is going to die. And if you have heard about the website called cscs.fi, this website, go to about, main developers, Antti Laksonen. And yeah, that is like cool. This guy made this CSCS website and also wrote this book, Competitive Programmer's Handbook, the same person. Shit, gotta justify my salary. I will keep in background running. Okay, thank you. Increasing my watch hour. I will get ads in some time. That is cool. Tell the higher ups that you were waiting for AI to generate the code. So I think you can give that excuse maybe if you do not want to work there anymore. In a union find structure, one element in each set is the representative of the set. Makes sense. And there is a chain from any other element of the set to the representative. Okay, that does not make sense. In a union find structure, okay, in this unique structure, one element in each set. And one more thing, it was not stupid to spend like 15-20 minutes like we did thinking about the implementation, because it is difficult to figure out how to find a data, which data structure to use, so that we can quickly find out if two edges if two nodes are connected or not, and then how to unite them together. It took them like literally 15 years to figure out such a data structure. In a union find structure, union find, that name is also like unique. In a union find structure, one element in each set, one element in each set is the representative of the set. Okay, one element, one element in each set is the representative of the set. Okay, that is new. Okay, if we have a component like this, let's say all these things are connected, they are saying one element is going to be representative for all the elements in this component. Okay, that is crazy. So whenever we want to say this component, we want to refer to this component, we will say the component of node number 2. And when we want to say which component does this element C belong to, this node is 6 belong to, we will say it belongs to component of node 2. Okay, and there is a chain from any other element of the set to the representative, as we do see. There is a chain from any other element in the component to the representative to 2. For example, assume that the sets are these, and this would be the union find structure. Okay, this is the data structure. Okay, shit, that makes sense. That makes sense. If at least for the unite part. I think, okay, just after looking at this, I think we can just make uh, write these operations ourselves whenever we are checking for same. Since we have the location of this node, we can look at its parent, and we will keep going up till we reach the representative, and we will do this for both the nodes A and B, and we will look at the representative. Is the representative same for both the nodes? If it is not, then they are not in the same component. And whenever we want to unite two components, we will go to the representative of one, and we can just add this at some point. Like we can just if you want to connect 1 and let's say 3, we will go to the representative of 2, and we can go to representative of this node 3, and which is 2, and connect 2 to 1. So like this. We had this, and then we also had this. Let's say we want to connect node number 1 and 3. We will go to the representative of 3, and we will make a connection like this, and these are connected. But then again, the same problem which comes in a binary search tree, we might get a tree which looks like this, right? Which is basically a linked list. In some cases, we might get something like this. Maybe there are safeguards to prevent this. There might be safeguards to prevent this. Let's see what they are saying. But yeah, at least we know how these two functions are going to work. Same for same, we will find the representatives. For same, we will find the representatives and compare them. And for unite, we will just like add a new child. Cool. Okay. Hello. Long time actually no see. Lambda calculus in CS not maths. Okay. Let's see what is lambda calculus. Yes, long time no see. How is everything? I think you said you were sick or something. How are you now? More like meeting point of mathematics and computer science. That is cool. We'll start new lead code account. My streak fell off badly. Shit. And yes, David Goggins, they don't know me, son. What problem does this data structure solve? Okay, this solves the problem in Kruskal's algorithm. We need two functions according to the algorithm, which will tell us whether two nodes are connected to each other in any way or not. Initially, in Kruskal's algorithm, we begin with just nodes, and no nodes are connected to each other. And as you go on adding edges, at some point we will, let's say we get a edge which connects, well, let's say which connects these two, but these two are already connected indirectly like this, from here, here, and here. So we need a way to quickly figure out whether these two are connected to each other or not. That is part one. And then part two is, if they are not connected to each other, then we want to like store it or save it somewhere that these two are now connected and consider them in the same component. So for the first part, where we are checking if these two are in any way connected, we can do it normally using a lot of time by running a DFS algorithm on this and going through each node that is connected to this thing, and eventually checking if we ever reach the other node or not. And this is going to take O of n time, where n is the number of nodes in this component, and that is not very fast. This structure guarantees that instead of O of n time, we will take O of log n time, which is much better than O of n time. That is being solved. And also the second part, when we connect two nodes like this, treat them as connected. Like, remember now that these two are connected. How do we do that? That also is guaranteed by this structure in log n time, and it like literally depends on our structure. If this if we were storing these components as a set, and whenever we, let's say, connected one node from this set and one node from this set, we would have to take their union, and for taking their union we have to go through each node in this set and in this set, which is also O of n time, because we are going through every node in the sets. But this structure guarantees log n time here also, so that is a very plus point. Bro knows his every viewing person. It, shit. Well, you will get. I don't know what to say. Okay. I really do not know what to say, but yeah, grind lead code, and yes, grind lead code, and I really literally do not know what to say. And yeah, so maps. Are you saying that we can use maps to solving to find a way to? Yeah, we can use maps for these two functions, or we can use maps for what? Let's like look at what they are saying after this. We have seen what they how this union find structure is going to be looking like, and it is on. Wait, you can have a like it, I don't really know. Like, shit. Uh, if you know Technoblade, I think this is the. If you don't know Technoblade, then uh, and how serious is it? Yes, shit. That is the first question I should be asking. The most popular. What's the one that you use for competitive programming, Elo? Core Forces. But just 1 minute, we got something real serious. If you know don't know Technoblade, then Technoblade is like actually a very cool person. He also had cancer and he is right now like no longer alive, but his attitude or his mindset towards this whole condition was is very inspiring. And I think he explains it in this video where I have been, and yeah, you can like check him out, Technoblade, and just take care of yourself. Yep, just live the fullest, and maybe you can do something better than okay, you know Technoblade. Let's go. Technoblade never dies. Maybe instead of lead code, you can watch some David Lynch movies. David Lynch is pretty cool. Like instead of so, and yes, like instead of showing the shortest, we can instead map out all the possible paths connecting A to E. All possible paths. There is going to, since this is a tree, there is only going to be one singular path which connects any two given nodes. And for yes, in this thing, Technoblade, no shit. The website I use and a lot of other people also use is Code Forces for competitive programming. This one, we love techno. It's confusing it. Okay, yep. Code Forces use Code Forces. Yes, just live the fullest and I don't know how serious the second stage is, but yeah, just like do whatever you want and be cool and maybe not spend your time randomly watching random YouTubers from other country reading a normal like CP handbook shit. You still have a strong immune system. Shit, your body is strong enough to fight it and just don't lose hope. Yes, that is much better than I have been saying. Yes, don't lose hope and yeah, you are young and your immune system is better. And back to this. In this case, the representatives of the set are 4, 5, and 2. Yes, each set has one representative. Each set has one representative. And one more thing, you are new to this thing. What I would say is you can go to this website, CP31, if you are still in like watching. You can go to this website CP31. This has problems rated from the easiest problems, 800 rated problems, and you can eventually like go up and solve more difficult problems. So from this website you will get the problems, and for theory you can go to CP handbook. This book, this is the one that I'm reading right now. Yep. This book has stuff, and at least if not the more like later more complex topics, you can at the beginning read simpler things like introduction, time complexity, sorting, data structure, complete search. These are cool. Yo, okay, you have someone special in Japan. Do some coding, the stuff I love to do. That is pretty cool. Without self-trust and confidence, even medicines cannot do much. That is something my father always says. He's a doctor. Shit. Your father is a doctor. That is pretty cool. And yeah, self-trust, hope. I'll go to Japan next week and wanna spend some time there. Uh, arigato, not arigato. All the best in Japan. Japanese. Shit, not Japanese.
ではごきげんよう。
Deva Gokigen yo might. I think someone is new to CP. Code Chef is the best because it is easy questions, much easier than the easy questions in Code Forces. I mean, I haven't used Code Chef. I used this CP31 sheet, and these seemed like easy enough. And I'm saying I'm not very smart, so these might seem easy to someone else also. Yep. Back to spanning trees. This new data structure that we are learning about. Union find structure. In this case, the representative of the sets, yes. Here, what we have is each component has a single representative, and the second thing, each other member of that component has a pointer to the representative, is connected to the representative in some sense. Like 6 connected to 3 and 3 is connected to the representative. And then in this case, the representatives are 4, 5 and 2. We can find the representative of any element by following the chain that begins at the element going up till the parent. For example, the element 2 is the representative for the element 6 because we can follow the chain 6, 3, 2. Yep, 6, 3, 2. Two elements belong to the same exactly same set exactly when their representatives are same. Yes, like we were theorizing. 1 has representative 4 and 6 has representative 2, and they do not belong to the same set because they don't have the same representative. And the efficiency of the union find structure depends on how the sets are joined. Wait, yes, the resulting sets contain this. Right here, two sets can be joined by connecting the representative of one set to the representative of the other. Okay, and this can be done as follows. Okay, that is crazy because I thought maybe the way that we are going to connect these is one leaf is going to be connected to a representative, but they are saying no, that is stupid. What we actually do is, yep, we connect the representatives themselves, which is, I think this is better. This is better than connecting the leaves because this is now growing in width. This is not growing in the height, but this is growing in how much spread out the tree is. So that is cool. That is cool. We can now start working on implementing this without reading further on. We can start implementing this and then we can just check. Let's use a class. Find union find. What is the name of the data structure? Union find. Bad choices. Share. Yes, live does. So yeah, you can do better things. I'm here. So what are we doing here? Can someone tell me? Yes, here we are looking at spanning trees and a data structure which is much more appropriate to our needs. And one thing I hate about things like CP is they don't consider real life scenarios and factors in life like cache locality. How would they? cache warming and other minuscule things which result in massive difference in the scale of, wait, not in the scale of milliseconds, but massive difference. Okay, in CP, the massive difference which does affect how your performance is not how much faster your code runs. It does not matter if your code runs in like 2 seconds or 3 seconds. This does not matter. The thing that matters most is how many problems you have solved, which will not depend on cache locality and cache warming. It will not depend. How the number of problems you are solving will not depend on cache locality or any other optimizing thing. And also how fast you were able to get to your solution. Like after reading the problem, if it took you 15 minutes or 10 minutes, it does not depend on cache locality or stuff like that. And these are the things which matter most in competitive programming, relating to your skills, relating to your performance. Okay, so you are saying not the performance, but they don't teach us stuff. That is, yeah, that is a thing, but they can at least teach you how to think. And yep, see you again. If I don't come for a long time, maybe after a few months, n- no, I will not make assumptions. You will be here again, right? After you have come back from Japan or wherever you are from, wherever you will be, you will come back and you will say hello, and we will say hello again. What do you mean by sandbox learning? Sport. Yes, it is basically a sport, but it is telling you how to think. And yes, you will come back and we will just exchange hellos. We will say, nice to meet you in Japanese, and let's write our class. Union fine. Shit, we don't do this. Okay, what is this going to have? This is going to have a list. For each node, we need to know which node is it connected to, which we can just keep in a simple vector. We can have a simple vector, and if our connection is like this, if you want to represent, let's say, this subtree, we can just have a vector. Let's say this is index 2, and then we have index 3, index 6, and index 8. Index 2 will just say 2 because it is the representative. Index 3 will say 2, it is connected to 2. Index 6 will say 3, 6 will say 3, and 8 will say 3 because they are connected to 3. We can just keep a list. This is going to have a vector v, or let's say, yeah, v words. And now a constructor find, this takes an int n, the size, and this will initialize v. This will initialize v. How v n, no, v dot assign, there are going to be n things, and initially everything is 0. And now for n, shit, n plus 1, because there are n things, I equals 0. From 1, we will begin from 1, small 1 equal to n I plus plus, and we will say vi equals I. Or we could also use iota function here. Yes, let's use iota v dot begin and v dot end. From the beginning to end, fill fill the vector beginning from number 1, beginning from 0, then put 0 plus 1 to the next place, and then 0 plus 1 at the next place, and we will have 0 1 2 3, something like this, which is what we want. At index 0 have 0. That is our constructor, and it works. We can also go fancy and remove this from here and only define the functions here. Same takes an int a and int b and returns an integer, and void unite takes in a and b and it unites them, and then union find find int n. How do we define the constructor of a class outside the class? Or in outside the class in CPP? Okay, we also have to say that these things are public, because everything in a CPP class in a class is private. Okay, it is not like this. And then, okay, shit. Outside the class. My class, my class. Why can I? This is from 12 years ago. Class starts here, ends here. My class, my class. So this should be working. This also should be working, but it is not. Redefinition of union find. Who is doing that? By default, it is private. Redefin. How is this redefinition? Yep, that is cool. Hello. CP is fine and all, but you want to design a performance system. Your biggest concerns would be cache misses and memory cleanups, none of which things are tested or thought of in CP. Yes, they are not. But CP tells you, like, yeah, I'm not going to make the case that CP is going to teach you everything. CP is not going to teach you that, but CP can teach you how to think in a problem solving way. Okay, shit. If you don't come for a long time, we will assume you got a Japanese goth. Goth is crazy. Yes, goth baddie. How do we define a class declaration outside the class? Shit, makes sense. Okay, shit. Be because of these two curly braces, we were defining the constructor as empty constructor. And now this is declaration, this is definition, and that is why we are getting redefinition error here. Okay, so declare here and define here. Okay, cool. vector, not vector. Uh, this I think dot v dot assign n, and everything is 0 in the start. This works. Okay, and then iota v dot begin and v dot end 0 fill, and that is good enough. Now for the same add unite function, you can find same int a int b. Wait, this should return bool instead of int. Okay, and we need to find the representative. We will have an inner function which is cool, which is actually pretty cool. We will have an inner function which returns an integer called rep and takes in some number I. Can we define this function outside? And since this is private, we cannot define this function outside. Private functions must be defined inside the class. While I is not equal to vi, what we'll do is I equals vi. That is, I think, good enough. And then return I. So for 3, if 3 is not equal to the thing that 3 is connected to, which is 2, then we will say I, which was equal to 3, now equals 2. And then we will check if 2 is connected to itself. And I'm referring to this example. And it is. So we will return 2. Find rep. Okay, find the rep of both of these functions. So and our representative of A would be this dot rep for A. Okay, we can just call rep, and rep of B is return rep A equals RB. If they belong to the same component, this will return true, otherwise this will return false. And I never knew that the underlying data structure required for something as simple as Kruskal's algorithm is a bit like unusual, not complicated but unusual. Now void unit find for unite A and B. Unite these two. And how do we unite these two? We will find the representatives rep A, and in representative for B is rep for B, and we will connect one to the other. How we A is B, which means now A is connected to B. I think we are good. I think we are good now. Yep, we are good enough. Shade, and now, okay, I wanted to do this. Yes, that is write some pre-written code. I have some pre-written code here, code for finding the mod inverse, but these are functions. These are all functions, so I would have to call these functions to get whatever I want. If I want to find the mod inverse of some number x, when m is the number with which we are taking the mod, then we have to call the function. But now, since I have written here this thing as a class, just seems a bit cleaner to write stuff as a class. And I have seen in other people's code also things pre-written code written as a class. So that is cool. Okay. So when we get this, yep, yep, after sorting, we can just remove everything else. And before moving, I would like to go to the washroom. Yep, I will be right back in just 1 minute. And goth character, gothic. I'll be right back. 1 minute. And yep, I am back totally cool. And yep, stream is also not stuck. Cool. We now just have to write our Kruskal's algorithm. Union, find the class of the type of the class, and we will call this helper, and this takes in n. What is n? Good question. And n is side. What is e? That is even better of a question. And this. Okay, we have initialized our helper. Now we will like to go through the edges. For auto left, right, even though there is no left and right, the edges are unidirectional, but still, let's say left and right. And also we need a vector which we will return. Vector of type will come later. Response or spanning. Uh, the okay, we cannot use class template or argument detection here. We have to give in edge. Right now, if helper dot same L and R. If these two things do not belong to the same component, then spanning dot pushes back. Add this current edge to our spanning tree, and let's also have a total weight plus equals W, and also connect unite a left and right. Good enough. And then return spanning and let's see, compile and run. Everything seems to be connected somehow. Shit. We have how many edges? How many nodes in this? we have 6 nodes, we should be having 5 edges. Somehow we have more edges than we started with. Now we have all the edges literally in the same order. Why haven't you gotten rid of some edges? Which means our class is not working correctly. Yes, our class is not working correctly. Let's also have a other function called print, which just prints everything. For auto, no, just cout v. After here at this point, we will call the print function. Tell us how everything is connected, and okay, they are connected, but that is a very weird pattern of connection. Tell us how they were connected at the start, and then after each node that we add, how that connection changed. Okay, initially every node was a single component, then we connected edge 5 and 6. Okay, and right in the next step we connected these two. So if we were to make this thing out, initially everything was a component of its own, and then we connected stuff. Till now we have a connection like this, right? And then in the next step 3, we connected 3 also to 6, and then we connected 2 to 5. Wait, we connected 1 to 5. Which is wrong? Which is wrong? We connected 1 to 5, but 1 is already connected to 2. Our unite function is wrong. Of course it is. Yes. Now it is good. Now our function is good. Don't print it. Cool. Now we only have 5 edges, and the sum is 2 plus 3, 5 plus 3, 8 plus 3 plus 5, 13 plus 7, 20. Now we do have something that is working. 20. Here also 20. 20 is the minimum spanning tree weight. Then implementation, we can move on to implementation. There was a proposed feature in C, I think it might come in upcoming C standard, where we can do things like case 1 to 5. Isn't it called switch? And I'd use that for case 1 to 5 pretty good if you ask me. Wait, don't we use switch? Switch is already there in C. Times this is take to show, I don't know, the speed or the bit rate for the upload for this stream is pretty cool. There is lag is like very low, but I don't know what the comments. We can do case 1, case 2, case 3, right? Yes, we can do right now. But okay, share with dot dot. Okay, we are giving a range. Shit, I messed up. I messed up. Okay, unhide. Shit, I messed up. I actually messed up. Shit, I messed up. Okay, you were saying that we can use a range, which is cool. Which is cool. Range. We can use a range in Rust. We cannot use a range in C. We can use a range. Range would be cool. Okay, our data structure is working. And I like accidentally ended your life. I think it is fine now. You are unhidden. Misclick. Misclick. No intention behind it. Now on to the implementation, which we already have had a hands-on experience learning by building. Some people have it in their LinkedIn. Which is, I guess why, but it sounds funny. The union find structure can be implemented using arrays. Union, literally, which what we did. We also used an array, and I want to do a stream in which I would like to write classes, write classes which would be useful during a contest, like a class like this, which would be useful for writing Kruskal's algorithm. A class, I already have some pre-written code. Absolute sum. What the heck? I have a function for absolute sum. What is absolute sum? V size equals 0, sort V, and then prefix, find prefix. Shit, makes sense, I think. Prefix. Yes, yes, okay. Find the prefix and then makes sense. Makes. Wait, does it make sense? What is happening here? Yes. What will this function find? This is cool. Okay. What this function finds is we have an array which has some values, like, of course, arrays have values. And for this function, let's say v, ith element is represented by vi and jth element by vj. And if we want to find out summation I going from 0 to, let's say it is one index to 1 to n, and j going from I, yes, j going from I to n, and we want to find out the absolute difference of vi minus vj. This thing is what is calculated by this function. This is useful in some problems. I think there were two problems where this was useful. I don't remember what they were, but yeah, this is what is being calculated. Yes, in some stream, I want to just go through and write these things again as classes. This is written as a function, but writing a singular class which would have all of this code, would be cool. Diophantine equation, mod inverse. Mod inverse is more useful than other things, I think. And policy-based data structure. Power function. Primes. Sieve of Eratosthenes. Yep, sieve of Eratosthenes. Smallest prime factor vector. FV. Okay, Kruskal works. Kruskal works. Now, shade, everyone is laughing at you. There was an opinion of view delete option of view delete. Shade, okay, there was. Huh? Well, I can like just hide you. No, there is not. Drugs. Okay, that is a song. That is a song. Tame Impala song and a movie. Train Spotting. I hope this does not run because this will give me copyright. Retarded. And this is a movie. Like these are all the drugs names. If you want to like buy some, sodium, amytal, phenobarbine, nitrazepam, and we took morphine, dimorphine, cyclozine, codeine. Yeah, if you want to look for them, yeah, you can find drugs. No, it is not. Compile time is not calculated. Just no, compile time is not calculated. Just runtime, and we can use Intel. Interesting. What is that? Do the system? They just tell us. They don't tell us about the CPU. They just tell us what compiler is going to be used for the submissions. Here, GCC C++23 GCC. This compiler MSY. Shit, I think this means Windows. Yes, you can go to Punjab also. When classes reduce runtime speed, because then program would need to run a track of v table. Need to keep a track of v table. Simple instruction, multiple data set. But can you access it using like can you access it using a language like Python? Because a lot of people also write code in Python and it just works. So the problems that they give you, if their general O of time algorithm, whatever it is, fits within the time limit that has been provided, then it is good enough. You do not have to go too deep into optimizing at processor register level. It should work with what you have. Delete message. Oh shit. And place them back. Tool. I'm getting the effects of shit. Okay, I know that person from yesterday. And place back. Shit. And place back. 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 If you have a vector of, let's say, pair. Yes, if you have a vector, let's say, of pairs of integers, intent, and with normal pushback. Okay, I should write code here. With normal pushback for your pair of vectors, you would give number 1 and number 2. But with emplace back, you would give the arguments which you would give to the constructor of the pair. And here you would give 1 and 2 like this. I think that is what emplace does. Normally, pushback takes the element itself which you want to insert, but emplace back takes the arguments which the constructor of that element takes to construct that element. So yeah, that is cool. I think emplace back is a bit faster because this I think would require some copying or moving because we are giving a like an object, but this would construct the element at the right place directly, I think. But yeah, that kind of optimization is not required. It is like, nope, not required. And if Python doesn't support it, then why do I need to pay for that if my language support it? and but it is not required. That is like going too much into the weeds. Not required. It is better to use templates for large data. For large element types and data. Okay, and implementation. Yep, the union find structure can be implemented using arrays. The union find structure can be implemented using arrays. Yep. In the following implementation, the array link contains for each element link. Okay, link is the name of our array. Link contains for each element the next element in the chain or the element itself if it is a representative of itself. Yes, and the array size indicates for each representative the size of the corresponding set. Why is this required? This would be required so that when we are joining two representatives, we are join we are when we are joining two representatives, we have to decide. We have two representatives, one A and B. They have their own set. We have to decide which one is going to be the new representative. So I guess we will choose the one which has a bigger size. This would be the new representative. So the connection would be like this. And how would we keep track of size? Vector of int, size, and yep, here this and size. Size assign n and 1. Size is 1 for everything initially. So for same, it is same as before, but for unite, we have to decide which one to use as the bigger representative. If size of A bigger than size of B, then A will be the representative. We will say connect RB to RA. Else connect A to B. And after the connection is made, the size also changes. Yep, we will just say size of RA, its original size as it was, plus the size of RB. And here also size of RB plus equals size of RA. Cool. And this would not help us too much because we only have 6 nodes. But yeah, this is cool. Initially, each element belongs to the separate set, to a separate set. Yes. The function find returns the representative for an element x. The representative can be found for by following the chain that begins at x. Find x while x is not equal to link of x. X equals this is like literally what we have written in our rep function. Where is our rep function? Here. While I is not equal to vi, I equals vi, and at the end return vi. And here this is a private function which we are defining inside the vector. Can we not define a private function outside the vector? Define a function of a class not vector outside the class. CPP. I think we cannot. Yes, you can. Shade. Define a private function of a class outside the class declaration in C++. How? private. With that was easy. Okay, we can. I just assume we cannot. Yeah. While I is not equal to I equals vi return I. Okay, that works. The function same checks whether elements a and b belong to the same set. This can be easily done by finding their representatives and comparing the representatives. Same, find a and find b. If their representatives are same, say yes, otherwise say no. The function unite joins them. Find the representative of a and b and change a and b to their representatives. Makes sense. Okay, shit, that is also cool. And these little things are pretty cool. Instead of declaring a new variable like we are doing ra and rb, we can just update a and b because we don't care what they are. We just care about the representatives. And then for size, we don't have to have two if else statements. We can just swap them, and we will always have a as the bigger element. Then that is cool, and that is what we will do, because cool, we do cool. Same, and here also return rep a equals rep b for unite. Yep, do all this. A equals rep of a and b equals rep of b, but we cannot just write the same thing here because we need to have originality. They are saying a will always have a bigger size. We will say a will always have a smaller size. That is originality. If size of a is bigger than size of b, size is not a function. That is right. Size is a vector. If that is true, then swap a and b. Now a is always smaller, and v a equals b. We are connecting a to b, and size of b increases by size of a. Cool. And also let's print size just in case. Cycle of print. This is the connection, final connection, and this is the final size, and everything seems to be connected to node 6, which is crazy. Okay, and now what is the time complexity? The time complexity is, since we literally have to go through each edge, so e, and for each edge we are doing two operations which take time. One is operation like the same thing, and the other one is unite, and this takes log n time, this takes log n time. So in total each edge takes 2 log n time, big O. So big O of e log n, which is good. If we take number of edges is nearly same as the number of nodes, then we can say big O of n log n. which is a good time complexity to have. Okay, and now we can move on to Prim's algorithm. What is the time complexity of the function find is log n, assuming that the length of each chain is O log n. In this case, the function same and unite also work in log n time. The function unite makes sure that the length of each chain is O log n because they are always connecting the representatives. So they have not written the final time complexity. That is fine. To avoid copy, as far as I know, vector copies unless you use move semantics. So if, for example, if we have a vector vector of pair of integers like this, let's say p, and we do p dot push back and say 1 2. This 1 2 is a pair, and this will be copied to the place that p is at, which is crazy. And I think the effect would be much more visible if we have a 2D vector like this. And I think maybe since we are giving an initializer list, maybe this might bypass the copying, because this might be used, this initializer list might be used to construct the element in place. Or maybe shit, since we have a vector here, we would be using pointers, or internally pointers would be used anyway, so it does not really matter. I think does not matter where this is, we would be using pointers anyway. We are here giving a literal, and literals are cool. I think literals are cool. But if we were to say something like this, I think now we are in trouble. Let's ask someone. CPP, I want this. Does the vector given to the push back function, or like grammar, is the vector given to the pushback function being copied to its final place in P vector? Short answer, yes. Shit, that is bad. Long answer, copied or moved depends on context, but in your exact code, it is a move which still involves copying the elements. Let's unpack this. No hand waving. Code. This, what actually happens, a temporary, this is created. R value is called with a R value. Okay, there will be different there will be different, what is this called? When we have same function called with different parameter types, what is this thing called? Overloading. Since we have function overloading, this pushback function is defined for taking a R value and also for taking a L value, and this, in this case, we are giving it a R value. What is a R value? R value is a value which is just a value and does not have a variable which is pointing to it, and this vector does not have a variable pointing to it, so this is a R value. Okay, pushback is called with a R value. The argument is a temporary, that is an R value, so its overload is selected. move constructor is used. When we give a r value, move constructor is used. Since the argument is an r value, this isn't, this is move, this thing's values. Move constructor is invoked to construct the element inside P. That is cool. Does that mean no copying? Not quite. Be precise. What is movement? What is moved? The internal pointer to the heap buffer. The size, capacity, these are just a few. Okay, the elements themselves are not moved but are not copied one by one. After the move, the temporary vector becomes empty, or at least valid but unspecified. P0 now owns the original buffer. Reallocation of P. It seems like uh, what does it seems like? This is a r value. This does not have a variable pointing to it, and P starts pointing to these same elements, and only the metadata, that is the size of the vector and the pointer to the first element, those things are copied at the back of P. That is cool. That is, yeah, cool. It's really it is, trust me bro, when we make making when me making a performant program, these things matter. Okay, I trust you. Read the second message you deleted. That was the main thing. Except you read everything else. Share second message I accidentally deleted, or I deleted everything. Okay. This one. This will make it less verbose and easier to read, especially when you are converting a large case and pretty sparsely. Okay, shit. Also, I have noticed you don't really use some of the advanced modern, because yes, like smart pointers, R value reference, semantics, range. Yes, range is something that I want to like see. You write C style C++, that is discouraged. Uh, because I only read the C++ programming book by Björn Stroustrup, which is on C++11, so it does not have modern features. That is why I'm now reading C++17, and then I will start reading C++20 and then 23. This book by Nikolai Josutis, and shit, this is illegal to show. Like, no piracy. You didn't see that. Okay, and I think it is still copy, since that is L value. You need to use move semantics to move it. R value. Wait, ranges was not there. Ranges, smart pointers were there, and smart pointers are not required here, but ranges were not there when and CPP. Look at this. It came out in 20, C++20. Yes, I remember. Ranges were not there. They came out later on. I'll study them. I do use transform. But the case when transform is required is not very common. Right? The conditions, the situations are not very common, but yeah, when I need, I do use transform. And what is transform? Transform is vector, and let's say this has, let's say, 20 elements, and we can say v dot. I think I've also made a post on transform. Include bits slash std c plus dot h vector of integers. Let's say v has size 20 and not this iota. We don't begin and we don't end. Start everything with zero. So right now, if we were to print v, we will see 1 to 20 numbers, 1 to 20. But using transform, we can change this. Shit. It is in algorithms, so which is inside this library. We dot begin and we dot end, given the start and the end point iterators, and for a specific element a, return a into 2. Is it okay? Nope, it is not okay. What is the syntax then? Output iterator. Okay. You also have to give which thing will be transformed. We can say dot start dot begin. Now in this case v will be changed, but if you want some other vector to have the new values, b v dot size, instead of v here we can say b. See out b will be twice for every element, 1 2, and for 20 we have 40. And we can remove v and here say v. Now v itself will change. Yep. This is also in JavaScript and other normal languages. Yep. 20. I never used transform. Yeah, the situations do not arise that often. And I remember ranges was, I don't know much about ranges. I have to study about ranges, but ranges was being used by someone's code somewhere, maybe Jiangli or someone. You don't have to pass it beginning or end to get ranges. Yes, shit, yes. We can use ranges instead of iota, right? Or something similar. Something similar. What rating are you solving? Right now we are just reading about spanning trees. We did Kruskal's algorithm and we learned about this new data structure called union find, whose name we will forget, but we will remember the concept. And now we should be moving on to Prim's algorithm. Transform, since I started learning lambda calculus and Haskell transform gives more of a function field. Yes, GS uses arrow functions like this. No, not for iota. The function programming patterns are quite good functional programming patterns. For I said not transform, but ranges. The functionalities which are provided by range, I think we can use iota for that. Ranges CPP reference. That is very big font. The ranges library is an extension and generalization of the algorithms and iterator libraries that make them more powerful by making them composable and less error prone. The library contains creates and Views, yes, shit, views. Views, I don't even know what views. There are string views. What are views? Basic is string view. This also came out in C++17. Yes. Mm, I don't know what this does. And okay, if you're going off topic, let's get back to Prim's algorithm. The next algorithm. Prim's algorithm also lets us find the minimum spanning tree, and before moving, let's copy this whole thing. Okay, see how we don't need this one. This class might be like useful, maybe. Kruskal, let's have a separate file. Data, spelling is correct. CPP, and yes, this is our first data structure, which is cool. You will find, and we will tell Lua print vector.cpp. Nope. Data underscore structures.cpp. Snippets.lua. Copy this instead of primes multiple. This is substitute primes to data structures, and data structures.cpp file boilerplate not used, yes, because it is going to be used here. Boilerplate primes, substitute last thing with the last selection with new create command. Do we want a command? Let's say, yeah, struct, and this prints boilerplate code for data structures as classes. And now if we were to go to Kruskal's algorithm here and type struct, we have the data structure magically printed here. So that is cool. Now we can move on to Prim's algorithm. Number 3, when did this come out? In 1957. The other one came out in 1956 by R.C. Prim. However, the same algorithm was discovered already. Shit. Yarnik. German? Yarnik? German person? No one remembers him. Czechia. Okay, he's from Czech Republic. Wait, you should watch Code Forces educational sections for disjoint union. Educational. Okay. I also have recently started using Move. It does make some good improvements. I was making SAX parser, whatever it is, SAX, and the improvement was about shit. That is like pretty good. And why such a big range? That is why such a big range? That is crazy range. And Code Forces education section for disjoint unions. See, edu shit. Yes, there were two courses, and I think one of them is like empty because it is not available in English. Is it just me or it is empty? It was empty before, but someone created courses here. These are for sparse table. Okay, we know about sparse table. Segment trees, part one, part. Shit, that is cool. Who is ITMO? ITMO is Code Forces. ITMO. Look at this. ITMO. Literally him. Is this a video? It is. Shit, that is cool. That is cool. They have suffix array, segment trees, part 1, part 2, binary search, disjoint set union, two pointers method. And this is good because they will teach us, or like at least for like revision, we will be able to revise or mm, see things in the way that code forces people see things, not just in some general way, which can be helpful. Yes, my bad. Because there were some mistakes I was doing wrong. Don't mind the range, mind the improvement. Lol. Yep, improvement is quite a bit, like from 10 seconds to 3-4 seconds. Okay, here, Prim's algorithm. Initially, there are no edges between the nodes. Everyone is empty. With they're just. Oh, shit, I skipped some stuff. Prim's algorithm 3 is an alternative method for finding a minimum spanning tree. The algorithm first adds an arbitrary node to the tree. After this, the algorithm always chooses a minimum weight edge that adds a new node to the tree. Finally, all nodes have been added to the tree and a minimum spanning tree has been found. This is like Dijkstra's algorithm. Prim's algorithm resembles shit. Okay, I didn't read this line before. Prim's algorithm resembles Dijkstra's algorithm. The difference is that Dijkstra's algorithm always selects an edge whose distance from the starting node is minimum, but Prim's algorithm simply selects the edge which is shortest among all the edges present at the frontier. Selects the minimum weight edge that adds a new node to the tree. When did Dijkstra's algorithm came out? And when Prim's came out in 57. What the fuck? Why is this the like first thing? When did he die? Nope. 56. Shit. The next year, Prim's algorithm came out. That is cool. Example. We can write this because we like know how to write Dijkstra's algorithm. Let us consider how Prim's algorithm works with the following example. They will go through this, and shit, that is the end of the chapter. Implementation. Okay, let's implement this thing on our own. Shit. Prims .cpp. Yes, that is a nice name. And, and how do we need things using edge as tuple int and vector of edge is going to be returned by prim, which takes in a vector of edge reference called edges, and this will have a queue of edges, queue of edges and Q is going to be the heap, a set. We need a set of edge. We will call it Q, which is cool. Okay, and then Q dot insert one. One does not make sense. How do we insert just one? We need to insert edges to this thing, and also we need bool visited size is, we cannot give a, yeah, we have to know the size beforehand. We cannot give a variable size to this. So vector in bool vector visited with dot size, and everything is false, right? Then we will say visited one equals true. We visited one, and every, okay, shit. So instead of a list of edges, having a adjacency list would be better here in this case. Vector of pair of, and this will just return the edges. That is fine. That is like, yeah, fine. And now for auto edge and weight, for edges, or we will call this ADJ, adjacency list. Substitute edges with ADJ. Which one? Yes, for one, and Q is going to be, let's talk about this. Yes, Q dot insert one, comma, one is connected with E with the weight W. While should we use a variable left, or should we look for, we will run this loop while Q is non-zero. But if we do run this loop while Q is not zero, it is not good to run this loop while Q is not equal to zero, and while size of Q is not zero, because in this Kras algorithm we keep adding the same edges again and again, and some edges we don't even want. So yep, having a left variable makes more sense here. Left, initially left is size minus 1, not just minus 1. Since the size of ADJ is going to be number of nodes minus 1, so this gives us the original size, and when we added 1, we will just do left minus minus, while left greater than 0, while there are people left, we'll take the smallest edge. And shit, how do we give our set function, how do we tell our set function what thing to sort by? Set in CPP. How do we give a compare function to a set in CPP? Can we? I think we can give it. We have our compare function and set of strings compare. Cool. Compare function is going to be like this. This takes in two two edges, edge A and edge B. return get element number 2 from A smaller than get element number 2 from B. Must be a type. Shit, must be a type. This must be a type, so struct. Shit. Okay, that is cool. This thing must be a type. We will have a type struct called just com. We could have said com. And here bool is returned by com, overloading this operator which takes in edge A and edge B. The problem, extra qualification number fix available. Okay, we don't have to say com. That is cool. Let's define this thing outside. It just looks cool. Bool is returned by operator this takes in edge A and edge B. Stop LSP. Yep. Now and here return get. Now this just looks much better because I have stopped the LSP. LSP was just getting in the way. Okay, and we can just pass this thing here. Form is a type. So now this works and set knows the compare function. Okay. So if you do auto auto left right wait equals q dot begin and go to that thing, we have this new edge from the frontier. Yep. And if both of them cannot be visited at the same time, if not visited L or not visited R, if at least one of these things is not visited, then we will visit, then we will visit this. Yeah, need a response. Distort pushback LRW and visited L equals visited R equals true. Both of these are visited, and we need what is the new thing that is being added right now. If let's say R is the one that is not visited, but if R is visited, then swap R comma L. So now we know that R is the one that is not visited, and we will add all the edges which are connected to R. So for auto E and W, for all the edges that are connected to R, ADG R Q dot insert R connected to E with a weight of W. Rest equals 0, and also at this point we know that we are going to add this edge or not this, that is error. LSP would have told us that weight plus equals W return this, and this should work. We will call prim. vector, vector, pair, and 1 to 3, and VDJ. First vector, second vector, pair, pair. Okay, how do we give in? No, we don't give in. Okay, this is the thing. Let's add all of these together. Okay, here we have, what do we have? Shit. Okay, this is empty. This is empty. This is node number 0. This is node number 1. We are saying node number 1 is connected to node number 2 with a weight of 3, and it is also connected to node number 5 with a weight of 5. Right. And then node number 2, node number 2 is connected to 1 with a weight of 3, and it is also connected to node number 5 with a weight of 6, and it is also connected to node number 3 with a weight of 5. Cool. Then we have node number 3. Node number 3 is connected to node number 2 with a weight of 5, and it is connected to node number 6 with a weight of 3, and to node number 4 with a weight of 9. The node number 4 is connected to node number 3 with a weight of 9, and to node number 6 with a weight of 7. And then node number 5 is connected to node number 1 with a weight of 5, and to node number 2 with a weight of 6, and also to node number 6 with a weight of 2. Finally, node number 6. Node number 6 is connected to node 5 with a weight of 2, to node 3 with a weight of 3, to node 4 with a weight of 7, to node 4 with a weight of 7. Okay, that should be good. We have our adjacency list. We can just auto, 1 second. Charging. This here, and this should be short. Cool. And we should get something like this. Okay, spanning equals call prim and give prim adj, and then for auto left, right, and w in spanning printf %d is connected with this thing with a weight of some number L R W, and hopefully this works and does not break. It does break. The LSV should be running right now. Is not. Unexpected initializer before makes. Does it make sense? What the- That does it. Q dot insert. Okay, there are multiple errors. Insert at unique position. Key static Q dot insert. Static assertion failed. Comparison must be invocable as gone. So I guess there constructor must be invocable as const internally, and const comes here, not there. Okay. Well, that was it. That was it. Shit. We are not decreasing left. Whenever we do add something, left decreases. No, it does not. Left doesn't decrease. What is left? Left should be initially equal to 5. Let's see. 5. It was equal to 5. And then it becomes 4. Cool. But then it doesn't change at all. Copy this. What is spanning, you might ask? Actually, is response and flush standard out. When do we added this edge? Cool. Visited are if shit, we are not changing visited. We are changing visited. Here also visited 1 equals true and everything to Q. Both of them are visited. Okay, which is not very good. Yes, shit. After this, uh, pop q dot remove shade, and so instead of this, we should be saying C and Q auto L R and W equals C and those C, and you got erase C. Yes. Okay, that was it. That was it. That was the problem. And the final answer here comes out to be 3 plus 5, 8 plus 2, 10 plus 10, 20, which is the correct answer. Which, yeah, where was it? It is the correct answer. 20 is the correct answer. And oh, that is commendable. That is okay. It, yes, okay. And for today, that would be it. We looked at a few things. We looked at Kruskal's algorithm, and we came to know about this union find structure. This is a new thing. This was a new thing. Now is not a new thing. And cool. This gives us new superpowers which we can use in different problems, in different situations. And we also know about Prim's algorithm, which is also cool. Tomorrow, maybe we'll do directed graphs, or maybe I might have something other planned. And for today, that would be it. And thank you for being here. Bye.